Hi all, welcome back to Dynamic Biosensor Labs. I'm Alice and today I would like to show you how to measure tight binder kinetics. In detail, we are going to measure the binding affinity between streptavidin and biotin. And to do that, we are going to use our heliX device. Here it is with me, and I think we are ready to start.
Affinity becomes challenging to measure for so-called tight binding ligands that possess low dissociation rate constants, Kd or O rate constant, where progress towards equilibrium is inversely proportional to Kd, necessitating prohibitively long pre-incubation times.
While there are methods available for the characterization of tight binders like streptavidin biotin, these methods are either 1. Established techniques that are suboptimal, like SPR and radiolabeling, which suffer from various drawbacks, including low flow rates and high technical barriers to entry, or 2. Ad hoc techniques that require high expertise and low throughput, such as chaser assays, droplet-based microfluidic platforms, and specialized FRET systems, among others. So far, either K-on or K-off have been discovered with high precision using these methods. With our switchSENSE technology, however, we can easily and reproducibly resolve both, and as a result, the correct dissociation constant can be discovered in a single measurement.
Our example molecule, streptavidin, is composed of a homotetramer with an extraordinarily high affinity for biotin. The binding of biotin to streptavidin is one of the strongest non-covalent interactions known in nature. Numerous crystal structures of the streptavidin-biotin complex have shed light on the mechanism of this affinity. Firstly, there's high shape complementarity between the binding pocket and biotin. And secondly, there's an extensive network of hydrogen bonds formed to biotin when it is in the binding site. There are 8 hydrogen bonds directly made to residues in the binding site, the so-called first shell of hydrogen bonding, and if we zoom in, the biotin binding pocket is hydrophobic with numerous van der Waals force mediated contacts and hydrophobic interactions with biotin when in the pocket, which is also thought to account for this high affinity.
Now let's have a look together what we really need for performing this tutorial. First of all, the reagents. Here we have 2 simple vials because this tutorial is really very simple. First is the ligand, that is our conjugated streptavidin. That is what we are going to functionalize on our chip. And the second is can be either biotin or biotin hydroxide, and we use it as an analyte. In this specific tutorial, I'm going to show you biotin hydroxide. One single concentration, but a long dissociation. After the reagents, that later on I will place it in the compartment of the reagents, so in the sample tray, we need our chip, our adapter chip. That, here it is, has 2 spots. One is for our measurement spot and the other one is our reference spot. I will go later in the details, but here we're going to place it here. Then after that, we definitely need our heliX instrument, and last but not least, the running buffer that I already placed it inside in our buffer compartment. This is a phosphate buffer. As you see, there is not so much, despite the fact we have more than 12 hours or 12 hours of dissociation time. This is ready, so I think we can continue and start our experiments.
The heliX adapter chip features a versatile linker system to immobilize and exchange molecules on 2 detection spots located in the same flow channel. The linker system consists of 3 building blocks, which are all made up of single-stranded DNA. The anchor is a 48 nucleotide DNA strand that is covalently attached to the gold microelectrodes of the chip via thiol chemistry. The chip comes pre-modified with anchors, which remain on the surface at all times. The 2 detection spots are modified with different unique anchor sequences, so they can be individually modified later by a technique called DNA-encoded addressing. The second element is the adapter strand, shown here in black. The adapter is a 96 nucleotide DNA strand whose lower half hybridizes to the anchor strand. The top end of the strand is labeled with a green or red fluorescent dye for detection purposes. The adapter strand is exchangeable and allows our assays to be very flexible. We can choose different fluorescent labels, different lengths of adapter strand, and we can easily regenerate the surface again and again. We can even integrate sophisticated DNA nanostructures such as DNA origamis. The third element is the ligand strand, which is modified with the molecule of interest. The ligand can be anything: a protein, a peptide, a small molecule, or even an RNA or DNA sequence. The heliX biosensor system can be used to measure 4 interactions simultaneously on a single heliX chip. This is achieved by using adapter strands labeled with either a red or green fluorophore, and they're targeted to either the first or second electrode. Red and green fluorescent signals are detected by single photon counters at each of the 2 electrodes. In the presence of analyte molecules, the fluorescence emission intensity of the dye changes by collisional and other quenching processes. The signal decreases when the analyte is bound to the ligand and increases again when the analyte-ligand complex dissociates. Whether the signal increases or decreases upon analyte binding is actually not important. What is important is that the signal change always scales with the fraction of analyte molecules bound to the sensor surface.
For this experiment, the ligand in spot 1 is a double-stranded DNA linked to streptavidin, while spot 2 will serve as a reference spot carrying only a ligand-free strand. As fluorophore, we will use a red dye in both spots. The workflow for this experiment is a classical switchSENSE assay workflow. First, we mobilize our streptavidin ligand strand on spot 1 and our ligand-free strand on spot 2. With our nanolevers prepared, we can then introduce our analyte, either biotin or biotin hydrazide, in the association phase. Then we will dissociate our analyte over the dissociation phase, which in this case will be 12 hours. Once we have completed the dissociation phase, we can then regenerate our surface to start another cycle. Since the experiment is pretty long, we are going to use only a single concentration of biotin equal to 200 nanomolar, just to ensure we have a saturated surface before dissociating. With this experimental plan in mind, I will now show you how to easily set up our planned tight binder assay in the heliX software.
Welcome to heliX. heliX instruments are controlled by heliX software, which is responsible for planning, performing, and analyzing your experiment. So the first thing to do once you want to plan an experiment, you need to go to the Assay tab and create a new assay. Today we're going to measure streptavidin biotin hydrazide interaction kinetics. So I type the name of my experiment, confirm the change, and then after saving the assay, I can start adding the measurement method of my choice. For these kinetic measurements, we're going to measure in static mode. So this is the tab, or let's say the measurement mode that I need to select. After adding the assay, you will see that there is a list of parameters, which is fundamental because it provides the device with all the information it needs to run my kinetic experiment and analyze it afterwards. So you will see that point 2, you can see that point 2 is related to the functionalization, so immobilization of your ligand that we can summarize with streptavidin, Assay, with a concentration of 100 nanomolar, and we don't need to regenerate the surface after each concentration because we are going to measure only one single concentration for today. Then related to the analyte, we already say that we are going to measure biotin hydrazide, and we are not going to measure the blank because we said that we use electrode 2 as real-time referencing. With a concentration of 200 nanomolar with one dilution factor and one count. It means that I just measure one single concentration. Then information related to the association, I type in 5 minutes for the association, flow rate we keep it 200 microliter per minute, and we use 720 minutes, which correspond to 12 hours for the dissociation. We keep the same flow rate for the dissociation, and another important parameter, since we're working with the dyes, is to use an LED power of 1 in order to don't stress our fluorophore link to the surface. Another parameter that we can modify is the sampling rate. Since we don't need to sample every second, so we can sample a bit less, so we can go down in the counting of the hertz.
Okay, then I think we are ready. This is nice that we can already have an overview about the sample tray that gives you an idea about how much you need and which are vials that you need to position in the sample tray. As I will show you in a second. I will put regeneration in position 1, I will have the streptavidin, our ligand, in position 2, and the analyte in position 3. And you have also very useful information because the system already gives you the volume that you need to locate, counting also the dead volume. Another important factor is that you have already an estimated time of your running experiments. In this case, we are talking about 12 hours and 30 minutes. Okay, I think we are ready to go. I will just put the samples in the heliX and we are ready to start. Now that our sample tray and chip tray have been ejected, we can place our sample in our chip. So let's start with the sample tray. This is our sample tray. As you see, you can locate the tiny vials up to 1.3 milliliters here in the first part. Then you have a big vials with 10 milliliter, and then you have the location for the 96 well plate or 384. Today, as you saw, we use just 2 tiny vials, so we just need position 2 and 3, nothing fancy. So in position 1, there is always the regeneration, and position A, there is the water. Position B, passivation, for the passivation on the chip surface, and C, there is the EDTA that we use normally for functionalization. So let's place our ligand, so the streptavidin, in position 2, as suggested by the heliX software, and then place biotin hydroxide, that is our analyte, in position 3. Here it is, very easy and very fast. Let's put it back and move forward for the chip tray. This is our chip tray. We can locate up to 5 chips, but today, as we said before, we just use position 1 with the first and 1 single chip. Let me just take it very quickly. Here we are. It's very easy and straightforward to place it because we have some magnets that help the position. So if you turn it, nothing happens. So you cannot do anything wrong, basically. Just let's put it back, and we're ready to start. Let's put back, inject back the trays, and we can start our long experiment. So now that our sample tray and the chip tray have been injected, we can move on our heliX software, which permits to control our system, design our experiment, and analyze our data to set up our tight binder kinetics. You will see it's a very simple and straightforward setup because, as I mentioned before, we will do 1 single functionalization with streptavidin, and then we will follow 1 single association of biotin hydroxide and a very, very long dissociation. We're talking about a 12-hour dissociation. So overall, we're talking about in terms of hands-on time, 10 to 15 minutes, so it's really, really easy. Most of the job will be performed by our heliX instruments. So now, stop talking, I will just show you exactly how to set up this experiment on our software, and you will see how easy it is and how it will be also very easy for you to set up your experiment.
After inserting the trays, now that they are in place, we go back to the assay setup where I plan my experiment, and I can already click Run. Before we examine the results of the assay, let's discuss for a moment the 2 phases of this and other interactions, the association and the dissociation phase. These phases are very different in tight binder systems, and to demonstrate this, we would compare 2 systems which both show a high affinity with streptavidin, biotin and biotin hydroxide. The association phase in tight binding system is often quite rapid, as we can see in both biotin hydroxide and biotin. Both curves demonstrate a good concentration dependency, but biotin hydroxide has a faster association rate. One thing that is very clear in these curves is that a longer dissociation time will be required, as no significant dissociation has occurred over 800 seconds. For the next section, we will choose 200 nanomolar of biotin and biotin hydrazide for a long dissociation to ensure we have a saturated surface before dissociating. As we have seen earlier, the dissociation of tight binders require a long time course in order to be measured. This is the primary reason why tight binders can be difficult to measure with other technologies. For tight binder interaction, it's clear that neither 10 nor 30 minutes are enough to measure a proper dissociation rate. As rule of thumb, you should dissociate until at least a 20% signal change has occurred in order to have a good approximation of the dissociation rate. This often requires a much longer dissociation time than other interaction, and many biophysical systems struggle to achieve this due to the low stability, high sample consumption, and in general long-term degradation. With switchSENSE, you can nicely measure at the same time fast association and long dissociation. And in addition, you can use spot 2 as a real-time reference, as we have in our assay, to observe and adjust for the signal drop that can occur over this long 12-hour dissociation, without the need of a blank run. The beauty of the system is that it's so stable that you can nicely discriminate the difference between two tight binders, and this is the reason why we decided to showcase two different systems, so biotin and biotin hydrazide. As you have seen it, electrode 2 is very constant, while the curve, especially the long dissociation of biotin, is definitely different with respect to the biotin hydrazide. If we have a closer look to the dissociation rates, you can clearly see that for biotin hydrazide we have a monophasic dissociation with a KD in the range of 1 to the -5. While for biotin we clearly see a biphasic dissociation, with the first part of the curve demonstrating an off rate 15 times faster than the second one. This experiment demonstrates the importance to measure above 5 hours dissociation time, because only at this time you can appreciate the slow dissociation rate in the range of times to the -6. And with this experiment we also demonstrate the ability of heliX biosensor to measure association and such a long dissociation rates at the same time.
Here we are on the last part of the tutorial, on the analysis part. And to analyze the kinetic assay, we need to open the finished experiment, either from the list of the experiment or through the experiment tab. With a double click, the experiment will be loaded, and for analyzing, you need to click on the blue button. Here we proceed, and we need to select simply the type of kinetics that you want to measure. In this case, it is 1-1 kinetics, or let's say that this is the fitting that we selected, and the fit model is incomplete dissociation. We don't have to forget that we don't have the blank, but we use only the real-time referencing. And after that, we can click Analyze, and in a few seconds we will get our data. And here we are. This is the finished analysis. heliOS is providing us with an overview of the recorded data, as well as a table with the fitted association and dissociation rates and the affinity constant, which in our case is equal to 2.7 picomolar. The increase on the fluorescence from the initial baseline during the association phase indicates that we have an anti-quenching effect on the sensing fluorophore by biotin hydrazide binding to the target. We indeed observed that the red dye interacts with the binding pocket of streptavidin, and once the association starts, biotin replaces the dye, and we observe this sharp increase of fluorescence. In addition, you may notice that 12 hours is not enough to completely dissociate our system. However, thanks to our mathematical model, we can clearly estimate the dissociation rates and therefore the affinity constant.
If we perform these experiments and the analysis across multiple heliX systems, we see high reproducibility across all the 6 units.
And if we have a closer look into the kinetic values obtained from those 6 different helix, we can clearly appreciate the similarity of the K values, with the KDs constantly around 2 picomolar, confirming once again the high reproducibility of the measurement mode and the stability of our heliX biosensor.
If we look closely at the slow off rate of these samples, the most important factor in tight binding, we observe that despite the very similar dissociation constant, because the faster on rate of biotin is balanced by the faster off rate of biotin hydrazide, they've very clearly different on and off rates. So in summary, using one biochip, 90 picomoles of analyte, 12 femtomoles of protein, and with 13 hours of heliX time, we've analyzed the binding of the streptavidin biotin type binder system and demonstrated how the high stability, sensitivity, specificity, and the real-time referencing of the heliX system allows for tight binding interactions to be characterized accurately and easily.
I think we're done for today, that's all. I hope you really enjoyed the tutorial, I hope it was useful, and I hope we were able to convince you that our system is very stable and can perform and define such a long off rates. If you want to try by yourself, or if you have another system, other tight binders like antibody interaction or so that you want to test by yourself, just please write us an email, we will be super happy to come back to you. And that's it, so ciao! Don't forget to subscribe to our YouTube channel and to check the other video. Bye!